All right. So last time we left off with Turing's work, specifically his proof that the halting problem is undecidable. There's no algorithm for it. And we started out by saying the set of algorithms is countable. One word, dovetailing. Right? You can enumerate all algorithms by size, and within size by lexicographic order. Give them numbers. Once you assign them numbers, all the natural numbers on one side, all the algorithms in C are on the other side. Big table, dovetailing, just like we did for the rational numbers. So we enumerate all algorithms or programs, which makes the total set of algorithms a countable set. It's infinite, but it's not as largely infinite as the real numbers, only as largely infinite as the natural numbers or the integers. Any questions about that result? So we're good on this? All right. Then we proved using diagonalization that the set of functions is not countable, even for Boolean functions. Towards contradiction, imagine that there's a table listing out each and every Boolean function in the universe. Never mind which order they're in, they're just in some order that claims to enumerate them all somehow. And we proved that it's no good. You can't do that because you can go down diagonal and coming up using the diagonal negated with a Boolean function that is not equal to any one of the rows, which means that Boolean function in red down here is not in this table no matter how this table is arranged, which means there's always ones missing, and therefore the number of Boolean functions is not a countable set. The set of Boolean functions is not countable. That's a diagonalization argument. It's a non-existence argument. We proved that we're not a millionaire. And there's Cantor and Turing both smiling. Very powerful result. It shows you that you have more functions that you can shake a stick at. Not enough algorithms to go around. And that immediately says that some algorithms don't suffice to compute certain functions. There's too many functions, not enough algorithms. Okay. Any questions about that? So this is a brief summary of what we did towards the end of the last lecture. So the set of algorithms is countable, the set of functions is not countable. There's necessarily, therefore, functions, even Boolean functions, that are not computable by any algorithm. That was a big surprise. Until Turing, nobody really thought that could be. So every function that you can define specifically, unambiguously, exactly, precisely, has some algorithm to compute it somewhere, even if we haven't thought about it yet. Maybe it's a very complicated algorithm, but certainly some algorithm exists to compute that function. And he said, no. For many functions, there's no such thing. In fact, for most functions, there's no such thing. The vast majority of Boolean functions even are not computable. And that's just a Boolean function. It's not just arbitrary functions. Right? Okay, so we defined the halting problem to be that of given a program and an input, does that program halt on that input? Yes or no. It's a Boolean function. It's very well defined. A program either halts or doesn't halt. There's no middle ground. It's law of the excludes middle. And we started out showing that it's undecidable. But first, we wondered whether it's about the size. Because certain short programs don't halt, like this one. This one's forever, very obviously. This one halts, very obviously. Some, it's unknown. In fact, for operating system to be correct, it shouldn't halt. It should run forever. If your operating system ever halts, that's called a crash. That's not good. So it's not even that a correct program should always halt. Sometimes a correct program, like an operating system, should run forever and should not halt for it to be correct. All right, the point is it's not about size, because you can take arbitrary mathematical formulas and encode them as very short codes, 10 or 20 lines, maybe even 5 lines sometimes, such that the halting status of that piece of code is equivalent to the truth of the original mathematical formula or theorem or conjecture open problem. How many get this? And that's why the halting problem is so hard. It's not because the programs are complicated and too long to figure out. Even short ones, we cannot tell whether they halt or not. So it's really very fundamental phenomena. Okay. And we gave examples like the 3x plus 1 problem. We still don't know what's going on. And here's the proof. This is where we left off last time, the last 60 seconds. So we're about to prove that the halting problem is not decidable. So h is this Boolean function that takes in a program and an input and tells you what that program would do on that input. Doesn't mean it can it must run that program on that input. It can do whatever you want. It can do some analysis, complicated, some calculations. It can do some, who knows what, some AI-ish kind of thing. But at some point, when you give it some program and some input, this is the black box, this function S that solves the halting problem, this is what it does. It tells you if that program would halt on that input, if that program indeed ran on that input. And it says either yes or no. It's a Boolean function. So S is this black box that computes H. H is the halting problem, H for halting. And it does it correctly for every combination of program and input. Remember, the program is a string and input is a string. Strings can be enumerated in canonical order, dovetailed through, and so these also can be integers, P and I. But let's just say they're strings. A program is a string, and an input file is certainly also a string. All right, so S supposedly solves the halting problem correctly every time and always halts and gives you the right answer. Towards contradiction, we assume that such a subroutine S exists. In a minute, you'll see that it cannot exist. All right, so if it does exist, we can take a copy of it and put a little bit of wrapper code around that, like a little shell script. We'll call that shell script T. And T basically has its own parameter X. And we're going to take the input to T, which we just call X, it's just a variable name. And we'll feed it to S internally inside T as both P and I, the two parameters of S, P and I, will both get the value that came into T as X, the external value, into T, the input for T. And of course, S does its job, just like we said a minute ago, always says yes or no. But T will watch like a hawk what S does. And if S says yes, T will deliberately go into an infinite loop. Don't worry about this second, about why we're doing this deliberately. In a minute, it'll be obvious. So if T watches that S goes and says yes and stops, T deliberately goes into the infinite loop on purpose. On the other hand, if S says no and stops, then T just says, I'm done, and stops itself as well. And that's easy to do. It's just a few extra lines of code other than S inside T. So S is called as a subroutine by T. And you can do that. If you have a piece of code, you can call it as a subroutine. In fact, if you couldn't call subroutines, all of computer science will not be very useful. Think about that. Because you'll have to write everything from scratch instead of calling subroutines, even addition. So that will be no good. All right, here comes the kicker. We're going to feed T to itself and see what happens. And by the way, are you allowed to feed T to itself? Is there some sort of a type clash or some sort of a type error or something will implode if you do that? I mean, say you can feed an algorithm to itself as data. Yeah, of course you can. Give me an example from real life where you might want to feed a program to its very self as input. Think about that. We'll come back to that question. But it happens in practice all the time. Yeah. It's kind of recursive or self-referential, but even with recursive functions, you don't necessarily feed itself to itself. You feed, it calls itself, but that's not the same as running it with its own source code as input to itself, which is what we're getting at here. So here we're running T on its own source code as a big string. Okay, so short answer is yeah, you can do that because T is a piece of code. Why? Because S is a piece of code, supposedly. Towards contradiction, S exists, so if it exists as a piece of code, as an algorithm. And so S is a piece of code, then whatever's in T that calls S and then converts a yes to an infinite loop and a no to a stop, that's also a piece of code with a few extra lines. So T is also a piece of code, which means it's a string as well. And both S and T take strings as input, so yeah, you can feed T to itself. There's no big type clash here. It's not like we're trying to feed a shoe into an algorithm. That's a type clash. Algorithms don't run on shoes. They run on strings or input files. So that's a type clash. You can feed an apple to an algorithm. That's a type error. Right? But here there's no type error. Okay, so if T runs on T, here's what will happen. Both P and I will be assigned T because X is T. We're running it on itself. So the input to T is T itself. So X is T, so is P, so is I. So S will ask whether T running on T will halt. And if the answer is yes, it'll go into an infinite loop, which means it will not halt. So if T on T holds, T on T will not hold because it will deliberately know that via S and then deliberately go into an infinite loop once seeing S output as being yes. And that's a little disturbing, but it's not a complete disaster yet, because what if T on T doesn't hold, on the other hand? So if T on T doesn't hold, T fed into T will take the value of X, which will then become P and I, so P and I will both be T, and S will tell you what T on T does, but now it doesn't hold. So S will say, no, it won't hold, but then T will observe that no and make an immediate stop, which means T just halted. So if T on T does not hold, it must hold. And that's now doesn't look very good in terms of logical consistency, because what we have here is a statement that says Q if and only if not Q. It means something is true if and only if it's not true, and that's a contradiction. So that's a logical contradiction, which means one of our assumptions on this slide was wrong. One of our assumptions was wrong. Now, which assumption on this slide is wrong? We assumed that a function can call another function as a subroutine. There's nothing wrong with that. That happens all the time. In fact, that's called programming. That's what happens all the time when you program. Routines call other routines, either explicitly or implicitly. Every time you say plus or times in your code, you're calling a multiplication or addition subroutine, and many other places too. So there's nothing wrong with that assumption that programs can call other programs. That you can take a formal parameter x and assign it to two internal other formal parameters p and i. This is an assignment statement, a couple of assignment statements here. There's nothing wrong with that. To observe a yes and then deliberately go into an infinite loop, well, it's not clear why you'd want to do that every day of the week, but you certainly could with just a couple of lines of code. You say if output equals yes, then begin and while true begin end, and that's your infinite loop right there, for example. So going into an infinite loop is easy. There's nothing subtle or wrong or questionable about it. Converting a node to a stop, again, that's an if statement. So what other assumption that we make on this slide? There's not a whole lot of assumptions here. And one assumption that we made that is not obvious is that there's a piece of code S that solves the halting problem and does it always correctly, always in finite time, always says yes or no, is always correct, always solves every instance of the halting problem that you give it. That is not so obvious. And in fact, that's the only assumption here that's wrong. So that's a proof by contradiction. S cannot exist as an algorithm, as a piece of code, as a Turing machine, as a program. It cannot exist. Because if it did, everything else will fall into place very quickly, and S and T can call S, and so on and so on, and all of a sudden we have this contradiction. So S cannot exist as a piece of code. It's a proof by contradiction. It's a form of diagonalization if you think about it. There's no table with a long diagonal, but if you think about it, you can concoct such a table and convince yourself that this is Russell's paradox in disguise. This is Pinocchio says, my nose will now grow. It's a non-existence proof. We prove that we're not a millionaire, that no algorithm exists, and it's sitting on the back of your Cantor's transfinite arithmetic arguments. In fact, diagonalization in this case. And implicitly dovetailing as well, because we mentioned that in the last couple of slides, which led to this. How many get all this? Any questions? This is subtle. It's not long because it fits on one slide. By definition, whatever fits on a slide can't be that long, otherwise it wouldn't fit on one slide. But it's subtle. It's mind-twisting. It's counterintuitive. We just proved that the halting problem cannot be solved using an algorithm. Not by us, not by anybody else ever. Not by an omniscient entity. They couldn't do that either. An omnipotent, omniscient entity could not come up with an algorithm for the halting problem. That's what we're saying. We're saying something very dramatic here, very encompassing, very far-reaching. Any questions about this? Ask me a few questions. If you don't ask me anything on something this subtle and this disturbing, then you haven't wrapped your mind tightly enough around it. Something, after decades of thinking about this, since I first saw it when I was a student, it still seems a little weird to me. It's such a short proof. It's so far-reaching and encompassing, covers so much ground. and establishes that there's no possible algorithm for solving something as simple as whether a program halts or not, which is the simplest question you can ask about a piece of code. Never mind what the code does, whether it's correct or not, whether it's useful or not, whether it's viral or not, whether it'll make money or not in the marketplace. Just simply whether it halts or not. That's it. That's the whole question, and that's not doable. So imagine how much harder the other questions are about code if you can't even solve the simplest question about a piece of code. And of course, all these other questions are also undecidable. We'll get to that later. All right, so back to the question, when do we want to feed a program to itself? Is that something weird, or is that something that you actually want to do in practice? And let me give you a hint. It's the latter. Give me an example in practice where you want to feed a program to itself. Quine, okay. Self-printing program. What else? Something very practical. Companies do this all the time. Yeah. Compiler. Yeah. So you can compile a compiler using itself. So when you build a compiler, let's say you want to build the latest Java compiler. You can write the new compiler in Java, and it's a super duper optimizing compiler. It runs much quicker than the old compiler. It even produces better code, more optimized code, faster running code than the old compiler, but it's written in Java. Remember, it's a Java compiler that's written in Java. So is that a recursive problem that a Java compiler is written in Java? Not really, because you have the old Java compiler. It's not as good as the new one, but it compiles Java, same as the new one, except it's an older compiler. So you compile the new compiler in Java using the old Java compiler. Now you have an executable of the new Java compiler. But you don't stop there. Why? Why don't you just stop there? Why would you want to do that? It's already compiled. Because the new compiler is more optimizing. It produces better code, more streamlined, more lean, more fast code. So far you have a compiled version of the new compiler using the old compiler. But now you want to take this executable version of the new compiler and use it to compile the new compiler, and it will now compile itself once it's already executable by virtue of being compiled with the old compiler. So it's a bootstrapping process. How many get this? It's exactly what companies do. That's how you can write compilers for the same language in the language itself, because you already have old compilers that can handle the initial compilation before the second compilation. So happens all the time. And there's many other examples where you can feed a program to itself. And not only it's a perfectly valid thing to do, that's exactly what you want to do for very practical purposes. You get better code, better executables, faster running codes. So not only that technique of feeding something to itself is not weird, it's actually practical and useful. So I just wanted you to be aware of that little piece of wisdom. So infinite loops are very hard to detect, in fact, impossible to detect. That's basically the bottom line. So how many have had infinite loops in your program, and you weren't sure why, you try to get rid of the infinite loop? Now you know why it's so hard to debug infinite loops. Now you know it from a mathematical point of view. It's not just a bug. It's a bug that's impossible to detect algorithmically. So if there's no algorithm in the universe to detect an infinite loop, chances are you'll have a hard time too. So now you know. All right, now we're in a position, remember that Venn diagram about numbers, the integers, the naturals, the rationals. This Venn diagram, it contained all the numbers, and we talked about quaternions, sedentians, octonians. So real numbers, we talked about circumplex numbers. How many remember that discussion from a few lectures ago? Okay. And we said a couple of things here that now we're in position to prove. Now we have enough mental infrastructure and concepts that we can actually prove these two theorems that before I just stated. Remember I said we didn't have enough machinery to, now we do. So first theorem, some real numbers are not finitely describable. So there are some purple numbers in this region that are reals, and they're reals because they're in this purple oval. That's the real numbers. There it is. But they're outside the finitely describable numbers. Numbers that have finite descriptions. What do you mean by finite descriptions? Quote, describe, 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 unquote. That's a finite description. You can either use English, code, symbolism, hieroglyphs, a video and YouTube, whatever is the description that you want to put between the quotes, as long as it uniquely defines the number in question. So even pi is finitely describable. pi is simply the ratio of the circumference of a circle to its diameter. There, I just defined it finitely. I described it and stopped, and now you know exactly which number I'm talking about. Pi. Not e, not the square root of 2, but pi. So pi is a finite description, so is the square root of 2. They also have infinite descriptions. Like pi is 3.14159, blah, blah, blah. But that's irrelevant because it's also have a finite description. The point is, some numbers do not have any finite description whatsoever. The shortest descriptions for them are infinite. And they're perfectly valid real numbers. How could you prove this? Tell you what. Prove it in one word. What technique are you going to use to prove this interesting theorem? That some real numbers do not have a finite description. One word. Diagonalization. How many see that is right? Yeah. Now somebody else expand that word into a whole sentence. In what way are you going to use diagonalization? How is that going to work? Vague, but silence is not a sentence. Unless you're a Zen master, in which case silence could be an entire novel. But how are we going to use diagonalization to show that some real numbers are not finitely describable? There's no finite descriptions for them. Use dovetailing kind of argument too, if you want, as part of your explanation. Note takers? If I give you extra credit for saying something, will you say something? Are you holding out for points here? Oh, see, over, yeah, good. See, the right incentive always works, yeah. Okay, assign values to strings, yeah. Yeah, so basically it's a lot like what we did earlier. A few slides ago, right here. You can enumerate all finite descriptions, put them in quotes, sort them by size, within size by lexicographic order, by dictionary order, and then number all the finite descriptions. So every description is just a sentence or a formula or just a string in general. It could be whatever you want in that string, but it's a finite string, so you can enumerate all strings by size, within size by lexicographic order. That's dovetail. So you can enumerate all finite descriptions. It means there's a countable number of them. Right? Because you just counted them, 1, 2, 3, 4, all the way down. Now the diagonalization part is there's too many real numbers and not enough descriptions. The real numbers are uncountable. Right? That's what the diagonalization argument says. In fact, there's the proof that we had a couple of slides before that. Try to enumerate all real numbers in a table, and you can't, because you go down the diagonal, construct a real number down here that's new and not in a table, and so the table was not sufficient. So you can never fit all real numbers in a single table, even though you can do that for the integers. All the integers are here, 1, 2, 3, 4, 5, 6, and so on. But all the real numbers are not there on the right-hand side, no matter what. Even if omniscient, omnipotent entity claimed that they were, they're not. It's too bad. Right? So that's the diagonalization part. Too many real numbers, not enough finite descriptions. So some real numbers are not describable finitely. There's too many real numbers, uncountable number of real numbers, only a countable number of descriptions, finite descriptions. So some real numbers are not finitely describable. Right? And that's what this theorem says right here. We just proved the existence of this purple point. We proved this region where the purple point is not empty. In fact, it's uncountably infinitely large. Not just countably infinitely large, uncountably infinitely large. How many get this argument? Good. Any questions about that? These concepts will be used over and over and over again to prove a great many things. So wrap your mind very tightly around these concepts, diagonalization and dovetailing, and these kind of non-existence proofs. Can somebody give me an example of a real number that's not finitely describable? How many can give an example? How many say you can't give an example by definition? Exactly, right? Now you're getting it. Yes, my Padawans, you're getting it. Very good. Yeah, you can't give an example because if you're good, that will be a finite description. And so it wouldn't be one of those things. That's not finitely describable. So by definition, we can't give an example of one of these, even though we proved there's an uncountable number of them all over the number line. They're not just rare, they're very, very common. Okay, good. So that's one theorem down. Now you see why I said a few weeks ago we didn't have the machinery in our heads yet to prove this, because we needed diagonalization and dovetailing and one-to-one correspondences and proofs of non-existence. But now we know about these things. Now we can prove such things quite easily. All right, second theorem. Some finitely describable numbers are not computable. That's a little more subtle, because the finitely describable numbers are countable. They're not uncountable. So now you can't use a pure diagonalization argument here because both are countable sets. The algorithms, the subroutines, the programs, the codes are countable, and so are the finitely describable numbers, both by dovetailing. You can sort them by size within size or lexicographic order, number them all down the line, and both the describable real numbers, finitely describable real numbers are countable, and algorithms are countable too. We already saw that. You can count or enumerate all possible codes, from the shortest to larger and larger and longer ones. All right, so anybody want to take a shot at this? And by the way, he gets extra, send to the class website your answer and you get extra credit. I'm serious about these extra credit stuff. And that it's good for you to speak up. Even if you don't say exactly the right answer, you get points for courage, which is good. You can't lose if you speak up. All right, so how would you argue that some finitely describable real numbers are not computable? There's a bunch of ways to do that. So let's look at one way to do this. So first of all, we already mentioned that some real numbers are not finitely describable. The real numbers are not countable. The finite descriptions are. Some finitely describable numbers are not computable. Here's the second theorem here. So the second theorem, lots of ways to do it, but here's one way to do it. Consider the following real number. I'm actually going to give you an example this time of a real number that's not computable. There's no algorithm in the universe to spit out digits of this number. This number I'm going to construct like this. Start with a 0, put a decimal point, then have these digits be h1, h2, h3, h4, and so on. And these are digits. They are solutions for the halting problem. Remember, the halting problem is a binary. It's a Boolean function. The answer is either yes or no for any input program that you give it, any input combination of program and string. So I'm going to take the solutions for the halting problem for successively larger and larger instances or inputs and put them all as digits in this real number that I'm constructing from scratch. And by the way, I'm combining the two parameters p and I into a single parameter by essentially Gödel numbering, which is dovetailing again. How? If I want to express program number p and input number I, I'm going to express both together as 2 to the p, 3 to the I. And if I give you the single value little I that is of the form 2 to the p, 3 to the I, where p and I are both integers, remember we can number the programs, like the people in jail who numbered all their jokes, and when somebody says 23, people laughed. Dovetailing in federal prison, not that funny, but still useful if you want to save time. So if you give me 2 to the p, 3 to the I as a number, I can uniquely determine both p and I from it. How and why? If you give me a number of the form 2 to the p, 3 to the I, how can I infer both p and I uniquely, unambiguously from that combined product of two powers? Power of 2 times the power of 3. What enables me to do that? It's not a trick question. It's very straightforward, but how could I do that? How many understand my question even? All right, so only 5 people understand my question. Well, okay, so let me ask again. Let's say I want to encode 2 numbers for you, P and I. They're both integers. And I want to encode them as a single number from which you can uniquely determine the 2 numbers, P and I. So I can't give you P and separately give you I. And what I also can't do is give you the product of P and I or even the sum of P and I. I can't give you the sum of P and I and from it expect you to uniquely determine what P and I are. Why not? Why can't I give you the sum and expect you to uniquely determine the 2 components that added up to the sum? Could be a lot of things. It's not unique, right? If I say 5, you don't know if it's 2 plus 3 or 4 plus 1 or 5 plus 0 or minus 2 plus 7. So from an addition, you can uniquely determine the 2 additive terms. From a multiplication, can you determine the 2 multiplicative terms? If I give you a number like 12, could you tell me what 2 things multiplied together gave me that 12? How many say, yeah, you can? We say, no, it's not unique. Again, it's not unique. So non-uniqueness is an issue here. So what I'm telling you is, if you take this number, 2 to the p, 3 to the I, from that you can determine uniquely both p and I unambiguously. How many get that? Good. And what enables you to do that? Keep dividing by 2 to figure out p, and keep dividing separately by 3 to figure out I, and I is the number of times you could divide by 3, and p is the number of times you could divide by 2 until you run out of 2 factors and 3 factors respectively. And which famous theorem enables you to do that? Let's get to the essence of it. So that's an algorithm, and that works. But there's a fundamental theorem of arithmetic that enables you to do this uniquely. There's a unique factorization theorem, right? Yeah, every integer could be factored uniquely into prime products. And that's also called sometimes the fundamental theorem of arithmetic, the unique factorization theorem. So that's what enables you to do that. So basically, you can take these digits and encode pairs of numbers with each digit. So h sub I is equal to 1 if I is equal to 2 to the p, 3 to the I for some integers p and I such that the program p holds an input I. So I'm encoding a pair of program and input as a single number, I. And if that program holds on that input, that single digit h sub I is 1, otherwise it's 0. And all the numbers here, zeros and ones for the h's, will encode all possible instances of the halting problem. How many get this? It's a dovetailing argument. It's a Gödel numbering. But this number here, once I constructed it, is a real number. How do I know it's a real number? Well, there's a 0, there's a decimal point, and there's a bunch of digits, 0 and 1. In fact, it's a real number in binary notation, using zeros and ones only. And it's finitely describable. How do I know it's that number? That number I just defined, little h, is finitely describable. Why isn't it just infinitely describable, but not finitely describable? Because I just described it in this one paragraph. And I stopped. And now you know exactly what this little number h looks like. How many get that? All right. So it's finitely describable because there's the paragraph that describes it precisely of what each digit is and isn't. But it's not computable. There's no algorithm to spit out digits of h. Why not? How do we know there's no algorithm to spit out digits of this little real number h that we just defined so finitely and precisely here? Maybe somebody else, the same 2 or 3 people keep impressing me, which is nice, but somebody new, say something. Yep. The halting problem. If I could have an algorithm that spits out digits of this in order, you can solve the halting problem using that algorithm as a subroutine. How? Take whatever input and program you want to solve the halting problem for, compute this I via raising 2 to the p times 3 to the I, And then you'll know which digit you need to wait on to see whether it's a 0 or 1 that will tell you whether that program holds on that input, whether program P holds on input I. Because if you have an algorithm that spits out digits of this real number that we just defined here, one of these digits eventually will come up and will be the solution to whatever instance of the halting problem you care to propose. How many get that? If you just wait long enough, you'll see enough digits, and one of them will be the answer that you're looking for. So if you have an algorithm that spits out digits of this, you just use it as a subroutine to solve the halting problem in general, which we know you can't do from the previous slides. So there's no algorithm that spits out digits of this real number either, ever, by us or by any other race, however omniscient and wise and omnipotent. Such an algorithm doesn't exist. It's like looking for the integer between a quarter and a third. It ain't there. But it's pretty obvious there's no integer between a quarter and a third. It's less obvious there's no algorithm in the whole universe to spit out digits of this real number. And there isn't either. Or to solve the halting problem in general, and there isn't one of those too. That's harder to show non-existence to, but we just did it. So it's pretty amazing. We just defined uniquely and unambiguously and pretty succinctly too a real number h for which no algorithm can compute digits of it ever. So it's a form of reduction or transformation. The non-computability of the halting problem implied the non-computability of this real number. And of course, there's many other real numbers that are not computable too. I just gave you an example of one, but there's an uncountable number. Because there's an uncountable number of real numbers, only a countable number of finite descriptions. And it's a form of Gödel numbering. And basically what we did is we just proved this second theorem here. We just proved that this red dot here exists, that this area where the red dot is here, it's not empty. And that little h on the next slide is this red dot. How many get that? And there's many other dots there too. I just gave you one example. There's plenty of others. So I'll give you another example besides this little h. I'll give you another real number that's also not computable besides this little h here that we just proved is not computable. There's no algorithm for it. This one is easy. And if you can't give me one example, give me 1,000. So I'm implying that if you think about thousands or millions or trillions of examples, you're probably better off than thinking about one more example. Actually, it's a big hint. How many understand my question? Not enough. Ask me questions about the question then. That's a meta discussion. So what I'm asking you is this. I just proved to you, we proved together really, that this real number h is not computable. There's no algorithm for it in the universe, ever. Not now, not by anybody. It's not computable, and it was a reduction from the halting problem. So that's what we proved, that there's no algorithm that spits out digits of h. And what I'm asking you is for another h prime, h double prime, that have the same property. There's no algorithm for that either to spit out digits of that. Yeah. Yeah. You can take this and divide it by 2. Or multiply by 3. Or add 5. Do whatever you want to it. Those are all uncomputable also. Why? Why isn't half that value or twice that value or 1 plus h, why isn't that computable? Let's say 1 plus h. Let's keep it simple. So if h is not computable, why isn't 1 plus h computable all of a sudden, mysteriously? Yeah, 1 plus h just puts a 1 there instead of a 0. And if you can compute digits of 1 plus h, you can solve the halting problem still. Ignore the 1, just look at the digits that are coming out of this supposed algorithm that spits out digits of 1 plus h. Wait for the right h sub I to come out for whatever your program and input is, and then you'll know the answer. How many get this? So 1 plus h is not computable either. Neither is 5 plus h. Neither is pi times h. Neither is h times e. Neither is h over 2. Neither is any arithmetic operation you want to do on h. That's also not decidable. Take your pick. The cosine of h is not computable either. How many get all this? So I just gave you millions of examples. Take any arithmetic expression you want involving h plus addition, multiplication, division, exponentiation, sines, cosines, whatever you'd like, square roots. You still get an uncomputable number. Because all these other operations are computable. Okay, any questions about that? So now you know millions of examples of numbers that are finitely describable, but not computable by any algorithm whatsoever. Let me ask you another follow-up question. Is pi computable? Let me say pi is computable. Let me say pi is not computable. Let me say pi is computable. There's only 10 people voting, so what's the problem with that question? Let's beat on that for a while. It's only 10 people voted. So ask yourself, is pi computable? Is e computable? Is the square root of 2 computable? Is 5 computable? How many say 5 is computable? All right, what do you mean by that? You just told me 5 is computable. What does that mean for 5 to be computable? What does that mean? You said it. You voted on it, right? Everybody raised their hand. So somebody say, why is 5 computable? Yeah, or even more simply than that, that prints out the value of 5. Say 5.00000, or you can just forget the zeros. Just say 5, end of story. So you just have an algorithm that prints out 5. That makes it computable. It's an algorithm that spits it out. That's all. It's as simple as that. Somebody see that 5 is computable. Good. Is pi computable? How many say yes? Pi is computable. Why is that? Make an algorithm that spits out more and more digits of pi. The longer it runs, the more digits it will spit out. They'll all be correct. None of the digits will be wrong. Same for square root of 2. Same for e. Same for 1/3. Just have it print 0.33333 forever. Infinite loop, but it prints correct digits. That makes it computable. So 5 is computable, 1/3 is computable, pi, e, square root of 2, they're all computable. H, not computable. It's not like pi. It's not like e. It's not like the square root of 2. It's definitely irrational. But it's not computable. It's worse than pi and e in terms of complexity or computability. Those are perfectly computable. H, not so much. How do we know that H is not rational? I just made this assertion. How many can see that H is not rational? 5 people, okay. I'll take it. Prove to me that H is not rational. Extra credit, you got 30 seconds, go. H is not rational. We'll wait for 30 seconds to give people a chance. How many see it by now? H is not rational. All right, take another 20 seconds. Give people a chance. How many understand my question? Good. I'm glad. I mean, the number is either rational or it's not rational. There's no middle ground here. What does it mean for a number to be rational, just to nail down that definition? Yeah, represented as a quotient ratio of 2 integers. Good. So why is H not rational? All right, how many have an argument, a proof? Okay, somebody new hasn't spoken yet today. Go for it. Yeah. Yeah, all rational numbers are computable. Somebody new, explain why he says that. He's right. Why are all rationals computable? Yeah, divide any 2 numbers that you want and keep spitting out the decimal digits of the division. Keep doing the division and more digits will come out, and it's rational, so it'll either terminate or repeat. That's okay. You're still spitting out correct digits by doing the division. How many get that? So every rational number is computable because simply divide and spit out the digits. This one, we already said you can't spit out the digits. There is no algorithm for it, so it's not computable. And if it's not computable, it can't be rational because we just argue that all the rational numbers are computable. How many see the whole proof end to end? So soon enough in this course, all of you will be able to come up with these arguments, instantly. By instantly, I mean in 5 or 10 seconds. It shouldn't be that mysterious to you once you get comfortable with these concepts. And so you see why we're harping on these concepts, because from these simple concepts of diagonalization and dovetailing and so on, you can immediately prove hundreds and hundreds of interesting, deep, counterintuitive even, theorems right away. Right? But you have to be agile and go through examples and wrap your mind very tightly around these concepts. They're very important. They'll come back again and again and again and again. We'll get incredible mileage from these concepts. Diagonalization, dovetailing, I can't emphasize that enough. So practice with those. Think about them. Work examples, work problems. Go to the sessions, go to the TAs, ask me stuff. Look it up in the book or anywhere else for that matter. Okay, any other questions so far? So we just proved this pair of theorems. All right. So all computable numbers are finitely describable. By computable numbers, we mean there's an algorithm that spits out digits of those numbers. That's what makes a number computable. It's an algorithm that just spits out digits, whatever notation you want, decimal notation, binary notation, you pick. So why are all computable numbers also finitely describable? Maybe there's a computable number that's not finitely describable. Just like we already saw on a previous slide, a real number that's not finitely describable. So why is it that all computable numbers, numbers that have algorithms that spit out their digits, are necessarily finitely describable? I mean, the answer is right there, but paraphrase it somehow. Yeah. Yeah, an algorithm is a finite description. Why is an algorithm a finite description? Because you start with a quote, and then you have a bunch of characters that comprise the program of the algorithm, and then you have a last quote. Before that you might have a last brace, if it's C or C++ or whatever. And that piece of code is a finite description. If nothing else, that is a finite description. You can also describe it in English if you want. So if you want to describe pi, well, you can describe it like the ratio of the circumference of a circle to its diameter, and from that it's enough to spit out digits using an algorithm, or the algorithm itself, the piece of code, could be a finite description, or some more complicated algorithm could be, or some mathematical formula could be that does the same, and so on if you crank it on it enough. So every computable number is also finitely describable. All right. Let's talk about the halting problem a little more so you don't have misconceptions about it, because it's so subtle, it's easy to have misconceptions about it. So what the halting problem says is that there's no single algorithm that correctly solves all instances of the halting problem. What it doesn't say that if you allow the algorithm to be incorrect on some instances, but correct on other instances, all bets are off. There's plenty of algorithms that do that. How many get that? If you're allowed to be incorrect sometimes, the task becomes easy, not just impossible, not just hard, not just moderately difficult, but trivial altogether. Explain that, why that's true. Why, if you're allowed to be wrong on some instances, you can solve the halting problem very nicely, very easily, with a very short algorithm. Somebody who hasn't spoken yet today. Let's get more people participating. Yeah. Yeah, exactly. Your algorithm can simply be, it always halts. End of story. Just one print statement that just says, yes, it runs forever. It never halts. That algorithm will be correct an infinite number of times. How many see that? It'll also be incorrect an infinite number of times. How many see that? How many lines is this algorithm? One line. So if you're allowed to be incorrect sometimes, and correct sometimes, and even if you have to be correct an infinite number of times, that's still a one-line algorithm. It's like the clock that stops, The clock there, it says 119. If it kept saying 119 all the time, it never changed. It'd still be right twice a day. How many get that? That's not saying much. So if a clock is allowed to be wrong sometimes, I have a very simple clock for you. Just write 12 noon on a piece of paper. There's your clock. It'll be right twice a day. It'll also be wrong a whole bunch of times a day. But now that's okay. So if you're allowed to be wrong sometimes, it's not at all the same problem as before. It's much more trivial and not very useful. Okay, any questions about that? So that's not what the halting problem says. But it's okay to be wrong sometimes and then it's still undecidable. Because if you're allowed to be wrong sometimes, it's perfectly decidable with a one-line piece of code. Like the clock that stopped on noon. It's correct twice a day. All right. So incorrectness in some instances is not allowed. Otherwise, the bet is off. It's not undecidable, and in fact, it's trivial. What if you allow an infinite algorithm, whatever that means? If you allow an infinite algorithm, you can imagine infinite algorithms, right? Can you give me an infinite algorithm that solves the halting problem? By the way, can a C program be infinite? Or a C++ or a Java program be infinite? How many say it could be, in theory? How many say it can't be, not even in theory? And you'd be right, it can't be. Why can't a C program be infinite? It has to be able to compile. So why won't an infinite program compile? Maybe it's a super fast compiler that runs infinitely fast. You're right, but let's nail it down real tight. Okay, you'll never reach the end. So how do we know the program, that infinite program, is not syntactically correct? If you can somehow argue that this infinite program is not syntactically correct, even if it reaches the end, it'll still be syntactically wrong and won't compile. Prove to me that an infinite C program cannot be syntactically correct no matter what. It's got at least one syntax error in it, and perhaps many more. Which statement? Return statement? Okay, it's getting there. What else? Yeah, the final curly brace. Remember, a C program starts with a curly brace at the beginning, and every curly brace has to have a closed curly brace. They must come in pairs. So if it's an infinite program, the final curly brace at the end of this program that matches the beginning curly brace at the beginning of this program, where is the final curly brace? Is it a mile down the road? Is it a light year down the road? Is it a billion light years down the code? Where is it? It ain't there. It doesn't just not show up. It ain't there to show up. That last character of an infinite program is supposed to be a curly brace. Where is it? Where is that last room in the infinite hotel? Is it down the street? Is it in the next county over? Is it a light year away? It doesn't exist. It's nowhere. It ain't there. And that last curly brace ain't there, which means the first curly brace doesn't ever get closed. That's a syntax error right there. Never mind what else is true about this infinite program. So programs can't be infinite. Algorithms can't be infinite. How many get this? Now, you can maybe concoct an infinite version of an algorithm by saying, okay, forget that curly brace. Let's invent a new language that doesn't even have this begin-end kind of pair matchings and curly braces that have to be closed or anything like that. Let's make an end run around this by saying, consider a big if statement. If, then, else, if, then, else, if, then, else. That goes forever. Just one if statement. That's your whole program. Can such a program with a giant if statement that goes on forever, infinitely long, can it solve the halting problem? How many say yes? How many say no? Split vote. Only 5 people voting, so I'm not sure what that split vote means statistically, but let me ask again. Let's say you're trying to solve the halting problem with an infinite program. That infinite program has the following structure. It says if the input is equal to x, blah, 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 then do something else. If, then else, if, then else, if, then else. Infinite nested if statement with if, then else, infinitely nested. Goes on forever. Can a program like that solve the halting problem? How many say yes? Good. He's right, you're right. Somebody else explain why. Expand that yes into a sentence so we're more convinced. Yeah. Yeah, basically that if will have every possible combination of input program and input string, and we'll say if the program is program number 1, the answer is no. Otherwise, if the program is program number 2 on this canonical list, the answer is yes. Otherwise, if it's program number 3, then it's no, then yes, then no, 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 yes, yes, yes. And you have infinite branches to accommodate all possible cases of possible inputs. That if statement will solve the halting problem, but that if statement is infinitely long. It's not a finite algorithm. How many see this? So if you allow infinite algorithms, all bets are off too. But algorithms can't be infinite. There's got to be a curly last brace. Algorithm has to end. But if you concoct some infinite algorithm, all bets are off and the halting problem doesn't necessarily apply to it. So I'm showing you the limitations of this result. It doesn't apply in all possible conceivable scenarios no matter what. It applies for finite algorithms, not infinite ones. It applies for algorithms which must be correct on every input, not incorrect sometimes, like the clock that stops at noon, that's correct twice a day, but that's not saying much about a clock. But it's still correct an infinite number of times. It'll be correct twice a day forever. But it's not a very good, useful, or interesting clock. Or if you allow infinite number of separate finite algorithms, again, all bets are off. I'll let you think about that one. Right? You can separate the if statement into just an infinite number of subroutine calls or whatever, and call them all in turn. Or if you're not required to solve certain instances, all bets are off too. The halting problem, this result, this theorem doesn't apply either. It only applies to scenarios where a single algorithm must solve all possible instances, not just some of them. Prove to me that that's true. That if you're allowed to not have an opinion as an algorithm, one way or the other, about some instances, yes, you can solve the halting problem. You can even solve an infinite number of cases as long as you're allowed to not solve an infinite number of other cases. Why is that true? Yeah, so give me an example of an infinite number of halting problem cases that can be solved with a very simple algorithm that doesn't have to worry about all the other cases besides those. Yeah, but let's just say this algorithm is never incorrect. It's correct on an infinite number of instances and voices no opinion on the others. So it's not saying anything wrongly about the other instances that it's not solving. It just is silent. It says, I don't know, if you wish. Yeah. Okay, good. So you can run the algorithm in question, the input instance program in question, for, say, a year of CPU time or a century of CPU time. If it halts by then, you say yes, it halted, or it halts, or it would halt, because you ran it and it halted. If not, if it doesn't halt within a century, you stop and you say, I don't know. Give me another answer. Besides, because this solution, correct though it is, it implies that the algorithm actually runs the codes. Give me a solution where it doesn't even have to run the code. It just has to be correct about the code, whether it would halt or not, if something ran it. Yeah. So you always default to a yes?
No, always default to an I don't know.
Oh, okay. Good. So if you always say I don't know, you won't be wrong ever. You're just saying you don't know. So let's modify the question to say you must be right an infinite number of times with a yes or a no. In other words, you can't just say, I don't know always, even though correct, strictly speaking, that answers the question. But let's modify the question so that you have to be correct an infinite number of times with either a yes or a no. And you can say, I don't know, but as long as you're saying yes or no an infinite number of times always correctly, you can say as many I don't knows as you want also, just not all the time. Yeah. Good. So look at the program and make sure it doesn't have any loops. No for statements, no while statements, not even a subroutine call to itself, which is recursion, which is essentially an implicit loop. Recursion is an implicit loop. How many get that? So no self calls, no loops, no go-tos, just straight line code. Arithmetic, ifs, whatever, but only straight line code, never branches to anywhere. All those programs will halt. How many see that? They have no choice. They'll run out one statement at a time and eventually peter out and halt, and that will be the end of it. So you can have a perfectly simple algorithm that detects non-looping programs and says each one of those will halt. And you'll be right an infinite number of times. It's not like the clock that stopped and says the correct time twice a day. Because you're correct an infinite number of times, not just twice. So the point is this. If some instances don't need to be solved, yeah, you can solve an infinite number of other instances correctly, and the halting problem and the halting problem theorem doesn't apply here. How many get this? So I'm showing you subtle cases, the limitations of this theorem. What it does, we already seen. Now I'm telling you what it doesn't do, where it doesn't apply. So don't go around thinking that every variation of the halting problem, no matter what, is unsolvable. Some variations are perfectly solvable. If you allow incorrect answers, if you allow infinitely large programs, infinite number of programs, or some instances to just say, I don't know, perfectly solvable. But always think about the clock that stopped at right twice a day. That's not saying much about a clock that is right twice a day. Or somebody that makes all sorts of bogus claims and occasionally happens to tell the truth. Not very impressive either. There's some politicians like that. But I digress. If you allow infinite running times, all bets are off also. Finite algorithm has to run in finite time, stop and give the right answer. It can't run forever and then give an answer. Why can't it run forever and then give an answer after the end of forever? Because there's no end to forever by definition, so the answer will never come. I can utter the words and make the noises. Don't make it true or consistent. Okay, so again, another limitation. Here's a cute one, but very valid. If you have a powerful enough oracle that you don't make any assertions to how it works, all bets are off also. So if I have a black box that has a little magic elf in it, infinitely wise, that always somehow knows the answer to any instance of the halting problem, this theorem says nothing about the elf. If it's got some magical creature in it, some gnome, some, I don't know, hobbit. Hobbits are not likely to think very hard and deep about mathematical concepts. They pretty much like to eat and leisure a lot. But, some magical creature that somehow happens to know the answers by magic, by divine, intervention, by some other mechanism that I don't even know what it is. It just works. The theorem doesn't apply. It doesn't apply to magic. It doesn't apply to magic elves, to gnomes, to hobbits, to whatever magical creature is in there somehow divining the answers. All the theorem says is that there's no program inside that box, that there can't be a piece of code there. No algorithm. It doesn't say that there's no magic elf there that somehow knows the right answers. How many get that? Even in Superman movies where Superman's supposed to be invulnerable, there's actually two things Superman is not invulnerable to. One of them is kryptonite. There's another. What else? It's usually not in the movies, but it's in the comic books. I'm actually an avid comic book fan as well. What's the other thing that Superman is not invulnerable to besides kryptonite? What do you think? We're in this context of gnomes and elves here. That's a hint. Magic. Superman is not invulnerable to magic, to spells, to potions, to Harry Potter stuff. So you'll put a spell on Superman, make him into a frog, or whatever, whatever wizards do with the magic. So you see the point, if there's some magic involved here, well, bets are off. The theorem doesn't apply. Question. So infinite number of algorithms. So let's say I have an infinite number of subroutines, one per every instance. If you give me the first program, I'm going to run the first subroutine, and it'll give you the answer for the first program. If you give me the 17th program in the canonical order, I'm going to run the 17th subroutine on it, and it'll give me the right answer. By the way, the subroutines will always either say yes or no. But you'll give me the program, I'll match it to the right subroutine of my infinite collection of subroutines, and that program will guarantee to give you the right answer for your instance. There, I've just solved the halting problem. But I'm using an infinite number of subroutines, not one subroutine that does the job for every instance. That cannot happen. How many get this? Good. Any questions about any of these? This is even more subtle than the original theorem. It shows you the limitations of that theorem. So even that theorem, expansive though it is, far-reaching and comprehensive though it is, that it speaks about any possible algorithm by us, by any other race of beings, by omniscient entities, omnipotent entities. That's saying a lot with one theorem. None of that can happen, but if you relax the problem in any one of these ways, including magic, the theorem doesn't apply to that. So even that theorem has some limitations. It's not completely encompassing in every possible different variation and scenario. It says a lot, but it also doesn't say certain things. Question? Infinite running time? Oh, good. So you want to know if a program runs forever? Then run it forever, and then you'll know. That's the algorithm. Run it for an infinite number of steps. And if it halts before then, you'll know it halts. If you run for an infinite number of steps and it doesn't halt, then you'll know it doesn't halt. After running it for an infinite number of steps. But what did I just say? I just said run it forever and then do something. But forever doesn't have an end. So that something else that I'll do after forever will never come. And so it doesn't make sense to say it. I'm just making noises with my mouth. I'm not being logically consistent. Good question. What else? All right. So Turing's paper lays all this out. 1937, 35 pages. It's the paper that founded computer science. That single paper, single author, is the most influential paper ever written, probably. Maybe with the possible runner-up being Einstein's theory of relativity in 1905 and Shannon's definition of information theory in 1948. But this leads the pack, probably. First defined algorithm for the first time in human history. Defined what it means to compute. Invented the so-called Turing machine model. And of course, there's many other models that compute as well. And they talked about universality, and a single machine computes the algorithm of any other machine by simulation, and proved that the undecidability of the halting problem is real, that this halting problem is not decidable, it's not computable by any algorithm. So everything we did today in this lecture is in this one paper. And this paper is so important. It also explicates the Church-Turing thesis that everything is intuitively computable is equivalent, that everything is computable also by a Turing machine if it's intuitively computable as well, and vice versa. So the notion of computable intuitively, like what the human brain does, and Turing machine computable, or algorithmic computable, or program computable, is the same concept. That's called the Turing Church thesis. And so this paper is so important, and at least once in your life you should see it. How many have seen this paper before? Okay, now you all have. We're going to go through every page of this paper in the next 5 minutes. I'm not going to harp on too many things except to say that, it talks about computable numbers may be described briefly as real numbers whose expressions as a decimal are calculable by finite means. It means algorithmically spitting the digits out. So right in the very first sentence of the paper, he says it. What we've been saying today, the whole lecture. Okay, and he talks about showing that computable numbers include all numbers that could be naturally regarded as computable. Okay, we're just going to highlight a few things for you from this paper. Very, very important paper. He says that numbers like pi, e, and so on are computable. Okay, but there's also numbers that are not computable. So he's not saying that it's not computable because it's like pi with many digits, because pi is perfectly computable, so is e, so is the square root of 2. We've been through that. And he talks about this model for computation that he calls computing machines. Now we call them Turing machines. Of course, when he wrote the paper, he didn't say they're my machines, him being Turing, but we now call them Turing machines because he's the single author of this entire paper. This is before he helped the Allies win World War II, by the way. It's 1936. Right? One of the most influential papers ever written. So here's the next couple of pages. He talks about automatic machines, which are Turing machines, calls them computing machines. He talks about how they work with a set of states and symbols and state transitions. And when we get to Turing machines, soon enough, we'll go into that in great detail. But he referred to them as automatic machines. And he defined them very precisely, very carefully, very unambiguously, with states and state transitions and symbols and alphabets and so on. And each one of these machines has tape and a read-write head, and the read-write goes on a tape and changes characters and uses the tape as scratch paper, if you will. And then he talks about computable sequences and what they mean, and he talks about the undecidability of the halting problem. He talks about the universal computing machine, which now we call the universal Turing machine. Another name for it is a compiler, right? You've used that every day, so you've used his universal Turing machine almost every single day of your computer science career, because it's just a compiler, basically. Compiler can do what any other program does based on the input that you give it. That is really your program, submitted to be compiled as one big string to this universal machine called a compiler. And he says very bluntly, right out front, that it is possible to invent a single machine which can be used to compute any computable sequence. So not only computable sequences can be algorithmically implemented and sped out the digits of, but a single machine, a single computer, a single algorithm can do the job of all of them, right? And one computer to rule them all. And that's the universal computer, the universal Turing machine, a compiler, basically. And then he talks about the definition of this universal Turing machine. He actually specifies it completely end-to-end with all of its states and transitions between states and so on, and that's the universal Turing machine. So basically, he's the first person in history to come up with a single machine that can do everything you can imagine. And now you have one in your pocket. It's called your smartphone or your purse. Your smartphone can do the job of any other machine, any other computer or algorithm. How? How will your smartphone do other things besides what it can do right now? One word, starts with an A. Algorithm. App. There's an app for that. What is an app? An app is a string. It's a series of digits, binary digits. You download the right app, and all of a sudden your iPhone could do brand new things that it couldn't do before, 5 minutes ago. It's called an app. He describes this right here. He didn't call it an app, of course, and iPhones were far away from being invented. But he gave a definition of a machine that can do the job of any other possible machine that you can imagine if you download into it the right string. And now we call these strings apps. Okay? So very, very insightful. Nobody's ever thought of this before. People thought before this paper that if you want a machine to do something else, you need another machine. Not the same machine. And in fact, you may even remember the days, it wasn't that long ago, that if you wanted to watch a video game, you used one machine. You used some sort of an Xbox or Game Boy or whatever to play video games. If you wanted to watch TV, you use a different machine, a television. If you wanted to do something, play music, you'd use a separate third machine called an audio system or a stereo system. If you wanted to edit text, you'd use a typewriter. That's a fourth machine. And so on and so on. You'd have all these different machines around the household doing different things for different purposes. And they're all separate machines. Now one machine does all of it. And it's in your pocket or purse. It's called a smartphone, or more generally a computer. It doesn't be a smartphone. It could be a laptop. It could be a larger computer. It could be a tiny little computer. But it does all these things. If you want your iPhone to play music, download the right app. You want to play video, download the right app. You want to do shopping, download the right app. You want to chat with your friends, There's an app for that too. That's what Turing is saying in this paper in 1936, before computers ever existed in physical form. Very, very insightful. He said basically one machine suffices, and here's the definition of this machine. And he tells exactly what it looks like. In 1936. And then, of course, he uses diagonalization, which he calls the diagonal process, but it's really just diagonalization. This picture I inserted. That's mine. The rest is Turing's. Because Cantor smiles, because everything Turing does is on the back of Cantor's diagonalization and dovetailing arguments. And he gives Cantor credit for that. Okay. So he describes the Church-Turing thesis as well. And we're almost at the end of the paper soon. It talks about the behavior of a computer at any moment may be determined by the symbols that it was observing in a state of mind. She talks about states or state of mind, right? What state the machine is in as it changes from state to state, as it observes characters on the tape and changes states accordingly and does computation as it goes. And he talks about Hilbert's functional calculus. Again, Hilbert shows up. Remember I told you Turing considered Hilbert one of his heroes, right? And he talks about more computable numbers and consequences of numbers being computable and not computable, and it gives large examples of classes of numbers which are computable and not computable. He talks about subroutines. He talks about a computable function of a computable function is still a computable function. So implicitly he's calling subroutines, which was another amazing invention. Now we take it for granted. And that's pretty much the paper. And he also gives credit to Alonzo Church for lambda calculus. And he shows that lambda calculus is equivalent to Turing machines. Okay. And that's it. So we'll pick up on this next time and keep going on computability, undecidability. Read the chapter in the book that talks about that.